So welcome students to this video, and here we are going to continue our study of fundamental matrices. Okay, see, in the earlier video what we have seen is if you have let's say phi. Okay, so first of all you consider the system, yeah, and please remember we are only talking about homogeneous system. Okay, consider the system given by x prime equals to 80 times x. Yeah, so we are not putting any initial data right now. Okay, just this system, and then what we have seen is the theorem which we did is the following, that if phi of x, okay, phi of x is a fundamental solution. Okay, it need not be a principal fundamental solution. Okay, it's just a fundamental solution, any fundamental solution. Okay, so if phi of x is a phi of t, phi of t is a fundamental solution, okay, of, let's call this 1, okay, of 1, then for any constant matrix C, right, C, which is a matrix essentially, yeah, so n cross n matrix, okay, phi t times C here is also a fundamental matrix, and any fundamental matrix, I will also show that any fundamental matrix actually looks like this. Okay, fundamental matrix of 1. Okay, so I should write fundamental matrix of 1. Clear? Okay, now let's see that so basically we know that this is the fundamental matrix. Now you see, therefore so any solution of any solution of 1, okay, how does it look like? Let's just write it down. Will be of the form x of t. So basically the general solution, we talked about it in the last video, right? Okay, so x of t will actually look like the fundamental matrix. What is, in this case it is phi of t times constant matrix C. Now please remember, this is a n cross n matrix and this is a n cross 1 matrix. Okay, this is the solution, not the fundamental matrix. Okay, right, any fundamental matrix will look like this. This C is a n cross n matrix, this is a n cross 1 vector. Clear? Okay, so this we proved in the last video also, yes, if you remember. Okay, now the thing is, any solution will look like this, so that's a general solution. So basically we call such a thing as a general solution. Now you see, so let me write it as n cross 1, so there is no confusion. Okay, and of course this is the fundamental matrix, okay, and so this is your general solution. Let me write, let's see. Now you see, if moreover 1 passes, okay, so 1 satisfies, let's just put it this way, 1 satisfies x0 equals to x0. Okay, I can put it at let's just put it at t0, so it will be more clear. So t0 can be 0, so x at the point t0 is, let's say, x0, so the vector, it passes through this vector. Okay, so this is in Rn. Then what happens is this, you see, x at the point t0, yeah, this is given to be x0, right, and if this is the solution, then this will actually satisfy phi at the point t0 as C n cross 1. So essentially we can actually calculate, that will imply the this constant matrix will be given by phi inverse of t0 times x0, right. See, x0 is a vector in Rn and phi inverse of t0 is a n cross n matrix. Okay, see, phi is a fundamental matrix, so phi is invertible, hence I can take the inverse of that. Okay, therefore the solution, okay, we know that the solution of this problem of x prime equals to 80 times x. Clear? x0, t0, let's just put it as t0. You can put it as 0 also, it is not a problem, but anyways, x0, x at the point t0, okay, will be of the form x of t. Okay, so please remember this problem, okay, this is in this form, right? X prime equals to f of t x. Okay, and we are assuming here all the time, it is in the whole entire course, we will assume that A is continuous n cross n function. Okay, so A is a continuous n cross n matrix, continuous n cross n matrix. Okay, so that is assumed. So it is continuous with respect to the t variable and C1 with respect to the x variable. So hence Picard says that in a neighborhood t naught minus epsilon and t naught plus epsilon, we can have a unique solution, and I have asked you to check that you can actually extend it to whole of the interval I, whatever this is defined, right? Okay, so with that in mind, so we know that there is a unique solution. Now the thing is this: how does the solution looks in terms of a fundamental matrix? We know that, you see, any solution look like this. General solution look like phi t times the constant matrix, right? And again, if it passes through x naught, then we know that what the constant matrix is this. So basically, the solution of this problem in terms of fundamental matrix will look like this: phi of t, phi inverse of t naught times x naught. Okay, so this is the unique solution. How do you get uniqueness? Unique solution by Picard. Okay, by Picard. Clear? So this is the solution in terms of, so let me put it this way. This one here, this one is the solution of a n cross n, okay, variable coefficient, okay, system, linear system, of course, linear system. So you have to have linear system, n cross n variable coefficient, okay, in terms of fundamental matrix. Okay, so basically in terms of fundamental matrix, this will be the solution. Clear? And this is a unique solution. So this part is clear. Okay, now let's look at the next part. Okay, so now we are going to talk about something called the adjoint system. Okay, to the equation x prime equals to at times x. Okay, we are going to define a new system out of this old one, and we are going to call it an adjoint system. Sorry. Okay, so let's look at see, first of all, we know. So let's start with this. Let phi of t be the fundamental matrix of the system x prime equals to at times x, right? Therefore, since it's a fundamental matrix, you can talk about the inverse of that. So define a new matrix. So define. Okay, you don't have to define it. So essentially, what is happening is, in that case, therefore, phi t, clear? Phi inverse of t. Phi inverse exists, right? This is going to be an identity matrix, identity n cross n matrix, that is clear. Okay, now you see what happens is, as I have already explained to you, the fundamental matrix which we are already getting it. Okay, we can talk about differentiating matrices, right? So we can actually differentiate this particular thing. So if you differentiate the above relation, we get, it is phi prime of t, phi inverse of t plus phi of t, phi inverse of t, the derivative of that, this is going to be zero matrix, right? Okay, so therefore what happens is, you get phi inverse of t, the derivative of that is nothing but minus phi inverse of t times a of t. Okay, I hope this is clear. You see, the thing is, why this is true? Because you see, phi is a fundamental matrix. So since phi is a fundamental matrix, okay, of, let's call it 1, right? That will imply that phi inverse of t is equals to at times phi of t. Okay, see, this is a matrix system. This is matrix differential equation. Let's just write it like this. Because you see, this is phi prime of t is nothing but a n cross n matrix. This is a n cross n matrix. This is also a n cross n matrix. Okay, so we are not in like this thing ordinary situation. This is a matrix differential equation. Okay, so if phi prime of t is nothing but 80 times phi t, okay, we put this phi prime of t here. So which is 80 times phi t. So that will give you that this whole thing, this expression is nothing but 80, right? Okay, so you can actually take everything on the other side and you can write it like this. Okay, so therefore we can also write it as, you see, phi inverse of t, okay, the transpose of it, okay, the transpose of it, and then if we take the derivative, this is nothing but minus a transpose of t phi inverse of t transpose of it. Clear? So basically, if I take the transpose on both sides, this is what I can write down, because transpose, the derivative goes inside, so it's not a problem. You can just write it like this. Okay, right? So if you are not convinced in this part, you take a 2 cross 2 element, simple 2 cross 2 element, and please check this part. Clear? Okay, so what does this gives you? You see, if you define, okay, I'm not writing that part, so let's just define this is as pi of t. Okay, so you see, pi of t will satisfy pi prime equals to minus a transpose pi, right? Okay, so therefore one can say, so phi inverse of t, okay, the transpose of it is a fundamental matrix, okay, of the differential equation, differential system, that is of the differential system. What is the system? In this case, it looks like x prime of t x prime equals to minus a transpose t x. Clear? Okay, and this system will be called the adjoint system of A. Adjoint system of, let's say, 1. Okay, so given a system 1, the adjoint of that system, okay, will be, so basically x prime equals to 80 times x is the original given system. The adjoint of the system will be x prime equals to minus a transpose x. Okay, we are going to talk about this thing later also. Yes, so please remember this thing, very important, this one. Clear? Okay, now we are going to look at a very important property of adjoint systems. So theorem. Now you see, if psi of t, okay, is a fundamental matrix, okay, fundamental matrix of the system 1. System 1. What is the system 1? This is the system. Okay, x prime equals to 80 times x. Clear? Okay, so let's start with the fundamental matrix of that system. Then let's try to put it this way: phi of t, okay, is a fundamental matrix of its adjoint system, if and only if, okay, phi transpose t psi of t is a constant matrix n cross n which is non-singular. So the natural question is this. See, the thing is, you are given this system 1, right? X prime equals to 80 times x, and we have derived another system which we are calling now. This is what we are calling it, the adjoint system of 1. Okay, right. Now the question is this: given this system 1, we know that there is a fundamental matrix for the system, right? Okay. Now the question is this: let us assume that what is the relation? So basically, you will have another fundamental matrix, let's say phi of the adjoint system. Now, what is the relation between those two fundamental matrices? That is basically the question here. Okay, right. So what it says is that if phi is a fundamental matrix, then psi is also a fundamental matrix of the original system. Then phi is a fundamental matrix of his adjoint system. And when is that? If phi transpose phi is a constant non-singular matrix, n cross n, of course. Okay, right. So let's look at the proof of that. Proof of this. So if phi of t, okay, is a fundamental matrix, let me write it this way. Yes, fundamental matrix of 1. Okay, it is given to us. Then phi inverse of t whole transpose. You see, we have already proved here. Phi inverse of t whole transpose is a fundamental matrix of the adjoint system. Okay, is the fundamental matrix of the adjoint system. This is what we proved in just now. Okay, system. Clear? Okay. So you see, what we have learned is this. See, the thing is, you remember any fundamental matrix, what is the first theorem which we talked about in the last video? So if phi of t is a fundamental matrix of 1, then for any constant c, phi t times c is also a fundamental matrix, and any fundamental matrix will look like phi t times c, right? That's what we proved. Okay, so you see, so if phi inverse of t whole transpose is a fundamental matrix of the adjoint system. Okay, so what is adjoint system? Given by, let me write it down, given by x prime equals to minus a transpose x. Okay, so you see, so now you see, if phi inverse of t, the transpose of that, okay, is a fundamental matrix of the adjoint system, then phi of t, so this fundamental matrix which is given to us, okay, this is psi, this is phi, right? So phi of t, the fundamental matrix of the adjoint system, is nothing, and this is also a fundamental matrix, that is also a fundamental matrix of the same adjoint system. So what did we learn? We know that it will be the transpose of this psi inverse t, the transpose of this times a constant matrix C. Okay, or let's just call it D. It will be better. Let's just call it D, where D is a n cross n non-singular matrix. Okay, how am I getting this thing? Matrix. How am I getting this thing? I am using this theorem. If you remember the theorem which we proved in the last video, this theorem. So if you have a fundamental matrix, another fundamental matrix will always look like the given fundamental matrix times a constant. Okay, so this is what I am using here. So therefore, you see, phi inverse transpose is phi transpose inverse, right? So if I take this on the other side, what do you have is phi transpose times phi of t is nothing but D matrix. Okay, that will imply, so if we take the transpose on both sides, it will give me that this is phi transpose of t, psi of t is D transpose. Okay, which will define it as our C, which is a n cross n matrix. Okay, this is what I will define. This is our C. Okay, so therefore, if phi of t is a fundamental matrix of the adjoint system, then you always have phi transpose of T psi of T is a constant n cross n non-singular matrix. Okay, right. And what about the converse? What is the converse? The converse says that if phi transpose psi is constant, you just have to show it is a fundamental matrix. Okay, so these you have to please check yourself. Please check yourself. This is not difficult, yes. Please check yourself. Okay, what do you need to check? You need to check phi of T is a fundamental matrix of the adjoint system. Okay, so basically what do you have to show? You have to show that phi prime of T is nothing but minus A transpose of T phi of T. Okay, I hope this is you can easily check this part. Okay, just put this value here and then you can actually see. Use the fact that psi of T is a fundamental matrix of the original system and you are done. Okay, so this I am leaving it up to you. I hope you can do that. Okay, right. So with this, what we are going to do is now we come to a section of this video where we are going to talk about something called a variation of parameter. Variation of parameter. Okay, so this is also known as the variation of parameter, method of variation of parameter. Okay, very important method, yeah, and we are going to use it in a lot of time. So what we actually know is this. First of all, let's start with a homogeneous system. Let's call it a homogeneous system. What is the homogeneous system? X prime equals to at times x, right? That's the homogeneous system given. Okay, and there is another inhomogeneous system. What is the inhomogeneous system? Is x prime equals to at times x plus b of t. Okay, please remember here at and bt are assumed to be smooth functions, smooth matrices. Okay, smooth matrix valued function, that is matrix. Okay, smooth matrices means these are basically matrices with all the entries smooth. Smooth means C infinity. You can assume it, don't worry about it. Okay, so I have a homogeneous problem and I have an inhomogeneous problem. We know that x of t, yeah, a general solution x of t, how does it look like? It looks like, so we know, okay, let me put it this way, we know that any solution, okay, any solution of the homogeneous problem in terms of fundamental solution, any solution of a homogeneous problem matrix, in terms of fundamental matrix, any solution of homogeneous equation looks like this. X of t is nothing but, let me write it like this, xh means x homogeneous is nothing but a fundamental matrix, let's say psi of t times a constant c. It's a constant n cross n non-singular matrix, constant non-singular, right? Constant non-singular. Okay, I'm sorry, this is n cross 1, n cross 1. Okay, this is a solution, right? It is not a fundamental matrix anymore, it is a solution. Okay, so that will be the fundamental matrix times a constant. Now you see, I want to find out if I want to see if we can find out a solution of the inhomogeneous problem using this solution of the homogeneous problem. So what we do is this. So let us assume that xi, we'll call it a xi is we'll say that this is a solution which will look like this. The fundamental matrix of this phi of t times a constant, but now constant is not it's not a constant matrix, but it's a matrix which depends on t. This c and this c has nothing to do with each other, right? So using, by motivating, getting motivated by this result, we were saying that since this x h looks like phi t times a constant matrix, we are assuming that the inhomogeneous problem, there is a solution which will look like phi t times a ct, where c is dependent on t. Clear? Okay, this is what we are assuming. We don't know whether such a solution exists or not. Let's just check if something like that can happen or not. And that is why this method is called variation of parameters. So we are varying the parameter here, right? Okay, so if that is the solution, what happens then? Then you see xi prime, what happens to this? This is phi prime of t, c of t plus phi of t, c prime of t, right? Now you see, if phi is a fundamental matrix of this, right? So what happens? And xi prime is nothing but at times xi, right? This is phi prime of t. What is phi prime of t? It is at times phi of t, and then we have c of t plus phi t times c prime of t. I will just keep this last expression as it is. Clear? Okay. Now you see, what is x of I? X of I is nothing but phi times c. So this is nothing but at times phi t times c of t, which is again nothing but at times phi of t times c of t plus phi of c, phi prime of t. Clear? Now this and this gets cancelled out. Okay. So essentially, I did some mistake somewhere. No, 1 second. Yeah. So this xi prime, since this is the solution of the homogeneous system, there is a b of t which I forgot to write here. So I should write it as b of t plus this. Yes. So I should write here also, there should be b of t plus this, right? Okay. So therefore what we get is b of t. See, this is the what am I writing here? I'm really sorry about it. This is c. This is c prime of t. This is c prime of t. Okay. So I have c prime of t is nothing but phi inverse of t. I made a mess here. So this is t phi of t. Okay. So c prime of t is nothing but phi inverse of t, b of t, right? So therefore what is c of t? Yeah, this is nothing but integral, whatever the integral is from, wherever it is, this phi inverse of s, b of s, ds plus some constant c. Okay, constant matrix, that is, it's a constant matrix, let's just call it this. Okay, right. So now if you see that what is our original equation, the original solution which we are expecting is xi is phi t times ct. Okay, so since therefore what is the inhomogeneous system solution we are assuming? We are assuming it is phi t times ct. Okay, and what did we get ct to be? We got it to be integral phi inverse of s, b of s ds. So integral phi inverse of s, b of s ds. Clear? Okay. Now you see, I can write down this c tilde, or I can just integrate it between t naught to t and then move this c in tilde. Okay. So let's put it this way, make it to be t naught to t. Okay. Now you see, so this is a solution of the inhomogeneous problem. Okay. Now, so therefore what is the solution of the general solution of the homogeneous problem? So the general solution of the inhomogeneous problem is given by what is it? xi, general solution. Okay, inhomogeneous problem general solution is given by phi t times c. Okay, phi t times c plus integral t naught to t phi of t, phi inverse of s, b of s ds. Clear? Okay, so you see why I wrote this. This is nothing but the solution of the homogeneous problem, right? It is xh. Solution, the general solution of the homogeneous problem. Let's see, this is the general solution of the homogeneous problem. So you see what I wrote is this, essentially the general solution of the inhomogeneous problem. Okay, inhomogeneous problem is nothing but the general solution of the homogeneous problem, okay, plus a particular solution of the inhomogeneous problem, right? You see, this solution which you got is a particular solution of the inhomogeneous problem. So the general solution of the inhomogeneous problem, what we are doing is we are just adding the general solution of the homogeneous problem with the particular solution of the inhomogeneous problem. So if you can find one solution of the inhomogeneous problem, then you can just add it with the general solution of the homogeneous problem, and put it together, and that will be your answer. Okay, now why is this true? Let's see. Let's say that y, okay, so why is this true? Question. Let us put it this way. Question. You see, if y satisfies x prime equals to 80 times x, okay, and z is a particular value, is a particular solution of x prime equals to 80 times x plus bt, okay, then you can see that y plus z, okay, is the general solution of x prime equals to 80 times x plus bt. Okay, how do you prove it? You just take the derivative of this particular thing, and you can easily see that this is true. Okay, so I am not doing this thing, you have to check it yourself. Okay, but this is trivial, this is actually trivial, there is nothing to prove here. Okay, so this is the fact which we are using here, and hence we have this formula. This is also called Duhamel's formula. Okay, please remember this is Duhamel's formula. We are going to use it all the time. So basically, any given solution, given a fundamental matrix of the homogeneous problem, any solution of the inhomogeneous problem, the general solution means any solution of the inhomogeneous problem will look like the general solution of the homogeneous problem plus a particular solution of the inhomogeneous problem. And how is that particular solution looks like? It is T naught to T, phi of T. See, this is independent of S, okay, phi of T. So you can take it outside. Phi inverse of S, B of S, ds. Clear? Okay. So in later videos we will actually compute this thing. So we will see that how can you use this formula to actually compute system of equation. Okay, but for that we need to know something called the exponential matrices and all. So in the next video we are going to talk about that, and then we will use Duhamel's principle formula to actually look at the general solutions. Yes, so with this I am going to finish this video.